Okay, hello everyone. So I'm going to be doing Q&A about science and technology, but specifically about things from science fiction. And I see we already have a whole bunch of interesting questions that have showed up here. Okay, the first one I'm seeing is, could our pets or other animals become intelligent enough to take over the world? That is an interesting question. So first question is, uh, well, first question is, how intelligent are pets? And what does that even mean? Because one of the issues is we humans made a very important invention. Maybe 200,000 years ago, maybe more than that, we invented language. And language allows us to communicate ideas in a way that is distinct. Okay, how do creatures learn things? So the most basic way a creature sort of learns things is through the way the creature is constructed, through its genetics. And there will be sort of built-in uh, behaviors of organisms that are not things the organism learns during its lifetime. They're things that are just built into the way its brain is constructed or whatever else. And we have a bunch of these. We have a bunch of reflexes where, the classic one is if you're hanging your leg out and you hit just below your knee, your foot will kick up a bit. And that's something that's a built-in feature for all sort of humans that are sort of working according to plan. That just happens, and it wasn't something any of us learnt in our lives. It was just something that was a built-in feature. So that's sort of the first way that learning gets passed down through a species, is through these kinds of just the construction of the organism. The second thing is kind of learning that happens automatically. Like, for example, when we're born, we don't know kind of how to see things, how to recognize objects, how to tell that's a cat, that's a tree, whatever else. We don't know any of that stuff. That's something that our brains learn, but we don't have to be explicitly taught that. It's something that happens because of the way that our brains are constructed. And when our brains are exposed to these different kinds of things that we see in the world, our brains sort of automatically make these connections. It's the same way that neural networks in modern artificial intelligence work. They sort of can automatically make those connections without us ever having to sort of think about doing it, without us having to kind of go to school to learn how to recognize a tree from a cat and so on. Those are just things that we see examples and we learn from them. It's an interesting question. If one of us humans grew up in a completely different environment with completely different things, without, on a moon base or something, where there just weren't any trees around, there were no pictures of trees, there were no, and it was all very different. How would, and we did that from birth. How would that affect the kinds of things that we know about, the kinds of things we can recognize, and so on? Well, so that's sort of the second level of how knowledge how organisms get to sort of use knowledge, is this kind of, their brains are constructed in such a way that when they're exposed to different things in the world, they sort of automatically learn about those things. So that's as far as sort of most organisms, so far as we know, have got, pretty much. Us humans have one very important extra piece, which is the use of language to communicate sort of abstract ideas, one person to another, without having to explicitly sort of, without having to just sort of see those ideas and automatically learn from them. This notion that we can sort of take a concept, describe it in words, like I'm trying to do right now, and other people can absorb that information. I would say, by the way, there's probably another level of this that is happening with computational language and computers and AIs and things, where not only are we able to sort of have one AI describe sort of perhaps even in something like human language to another AI what's going on, but the AI can actually, in a computational way, directly understandable by the AI it's communicating with, can communicate something. But that's sort of another level that's sort of for the future of our civilization. But the thing that really sort of enabled our civilization, I think, was the notion of language and the idea that one could pass abstract ideas down from one generation to the next. So that's the thing that I think, made our civilization kind of come alive, so to speak. And I think that's the kind of thing where you sort of need that to develop sort of the sophistication that, for example, our species shows on this planet. Now, there's sort of a question of, so we've developed, it's very convenient that we have, hands that, are good for grasping different kinds of things and so on. We have our opposable thumbs and all those kinds of extra good features. But I'm quite sure one could imagine sort of building a civilization out of, underwater things that you could move around with flippers and noses and things like that. I don't think you fundamentally need, opposable thumbs to build up all the things that we have in our civilization. Although the way our particular civilization has been built, the fact that we have door handles that work the way they work is a consequence of the fact that we have hands that work the way they work. If we didn't, if we had flippers instead of hands, we'd build door handles, we'd build doors differently, so to speak. But I don't think there's anything fundamental about civilization that requires, things like door handles. So it's, I think then the question is, when you look at animals, there's sort of this question of, well, to what extent have they already built up something that is kind of like the things that you need to build a civilization, and could they do that in the future? So I think the thing, well, first kind of question is, it's a common thing, not so much in science fiction, but more in just fiction books, like, I don't know, the Dr. Dolittle books, which I read when I was a kid, where it's like humans talk to the animals. In reality, we can, get some level of communication with pets and so on, but we can't really have a serious philosophical discussion with a cat, for example. The question is it conceivable that in the future we could have a serious philosophical discussion with a cat? Does a cat have what it takes to keep up its end of a serious philosophical discussion? Is the issue just that we don't know the right language to communicate with the cat? Or is the issue that the cat doesn't have the concepts that would constitute a serious philosophical discussion with us? We don't completely know the answer to that. I have a suspicion that it's a mixture of those two issues. That first of all, there's been no the understanding of what might constitute a language that we could use to communicate abstract ideas with animals. That's not really been properly developed, and whether I don't know whether it's a matter of brain construction or whether it's a matter of kind of if a cat from birth was kind of exposed to an environment where there were kind of abstract ideas being communicated, maybe it has a different point of view, so to speak. But I've kind of for humans we have these vocal tracts that allow us to make this whole range of different sounds. There are plenty of animals from parrots onward that have pretty complicated vocalizations. There are also perfectly well animals that one could imagine could learn to do sign language and things, and certainly some primates have been taught sign language. But there's nothing, there's, in terms of, is there the wherewithal for animals to communicate with us? Yeah, there certainly is. We had a project years ago that never really got off the ground, that involved making video games for animals. And sort of the thing was, imagine a cat, swiping at an iPad screen, or imagine a cockatoo, touching its beak to an iPad screen to be able to build things up. We don't know what, if you provided that kind of environment for animals, we don't actually know what animals would succeed in building up. We also don't know if we could let animals have a means of communication. We don't know what they would be able to talk about. Like, for example, our view of the world, for instance, that involves the fact that, we're walking around and we're using our hands to do things, and our eyes are pretty good, our noses aren't so good as sort of sensory organs and so on. Our ears are detecting sounds in a certain range of frequencies and things. We have a certain experience of the world. Animals can have very different experiences. Like, for example, they can primarily use smell to tell what's going on around them rather than primarily using sight and so on. And the question of exactly how we would sort of develop the common themes to have discussions with animals, not so clear. So, okay. So, but the original question was, could the animals become sort of more intelligent than us and eventually take over the planet, so to speak? The answer is surely yes, because, it's like our evolution over the last couple of million years has been no different than the evolution of other organisms. And we've managed to get to this point where we have language and we can do all these things and we can start sort of spinning up this whole civilization that we have and so on. Now, I mean, it's worth realizing that the forces that have led to sort of the progressive change of organisms in biology, those forces pretty much don't operate anymore with humans. So, for example, it's a very brutal business what's happened in the history of biological evolution. I think Charles Darwin, who developed this theory of natural selection, used to talk about it as the struggle for life. You have an organism, and the organism is much better. You have a particular type of let's say, a particular type of bird, and the bird has and one bird starts to have a beak that has a particular shape, and that particular shape turns out to be much better than the shape of other birds of that same type at cracking open some kind of nut that exists. Let's say that one bird is born that has a weirdly shaped beak, and that weirdly shaped beak is a lot better than all the other birds of that type at cracking open the nut. Okay, so that bird, it lives a happy life, it cracks open the nut, it eats more, then it has a bunch of children. And its children will tend to get the same sort of genetics as that bird with its funny shaped beak had. And so the children of that bird will tend to have funny shaped beaks as well. And those children will then be also successful at cracking open this kind of nut or whatever. And so what will tend to happen is that those children will then be more successful, so they'll tend to have more children and so on. And the thing quickly gets to the point where that funny shaped beak is the thing that makes those birds more successful, makes them have more children. And so the trait of having the funny shaped beak will quite quickly be the one that takes over in that collection of birds, because though the birds with the funny shaped beaks are the ones who have more children, their children have more children and so on. And pretty soon the funny shaped beak crowd takes over relative to the not funny shaped beak crowd. So that's been the thing that's happened throughout the history of biological evolution on Earth, 3 billion years or whatever it is, that there's been this kind of struggle for life, where organisms that happen to adapt better to the environment that's presented to them will have more children on average, and will eventually take over. Now, it's kind of complicated because one organism can interact with other organisms. There might be a whole cluster of organisms that all fit together in a particularly good way and so on. But that's the scheme, is the organisms that are somehow better for the environment end up having more children and sort of take over. With us humans, and it's a feature of civilization, we're kind of not in that situation anymore, because it's not the case that it's with the choice of number of children and so on is only weakly dependent on kind of things like if there was a trait of us humans that was just a really good trait for achieving some particular kind of thing. Let's say it was important that humans be able to have some particular attribute. I don't know. It became type faster, let's say. Let's say that was a thing that was really important for the environment. It's not obvious that there's a connection between that and the number of children one has and things like this. So the standard story of biological evolution doesn't quite happen in the same way for us humans, and that's a consequence, and I would argue it's actually a good consequence of civilization, so to speak. So this question of could the animals take over? Well, we've kind of got ourselves into a special situation where we're no longer subject to quite the same forces of evolution, and I think that for better or worse, that means that it's the animals taking over requires that presumably, well, maybe if we gave all of the wild turkeys of the world or something the ability, we gave them all, we gave them cell phones or something, and we gave them the ability to communicate with each other in some sophisticated way, maybe we would find that with that enablement, that the wild turkeys of the world would start getting together and creating some civilization with progressively more sophisticated capabilities, and then we might have, then we might have a more serious competition, so to speak, in terms of who's creating the sort of the future of the planet, so to speak. So I think that was a kind of a complicated answer, and I mean, it's a sort of complicated issue because at some level, well, yeah, okay. Let's see. Next question we had here was, what would faster than light travel look like visually? Because I've actually think that I have a pretty good idea of what the fundamental theory of physics might be like, I've been thinking recently about faster than light travel. So first thing to say is, normally in most modern theories of physics, light is in a vacuum is the thing that travels as fast as anything travels. Nothing, according to current physics, can travel faster than light. Now, there's a slight footnote to that, which is light travels in straight lines where the straight lines are defined by the structure that light sort of, that space has. So if space has some really weird structure, when light is kind of going in a straight line as quickly as it can from point A to point B, it might not look like a straight line to somebody else because space might have some more complicated structure. That's what happens when one has curved space that's that represents the gravitational forces and so on. But one of the weird things that's been talked about for, I don't know, 50 years or so now is this idea of what are called wormholes, where you might have space and you might have kind of a wormhole where there are two pieces of space, two things which normally are separated in space, but there's this kind of wormhole, like a worm digs through the soil, where you go in at one end of the space and you come out at the other place in space. And you are kind of going directly through this wormhole. You don't have to go through all of the space on the top of the soil, so to speak. You can just go through this hole that the worm made underneath the soil to get from one place to another. So actually, I have a new version of this I just invented a few weeks ago that I'm calling space tunnels. And we normally live in space that is three-dimensional, roughly. We can go left, right, up, down, front, back. But it's possible that the universe and the laws of physics actually would allow different numbers of dimensions of space as well. That 3 dimensions is just what we happen to have, what happens to exist mostly in our universe. So the weird potential idea of a space tunnel is something where, for example, you have a higher dimensional piece of space where normally you're just going through space, you have to go through the standard 3-dimensional space from here to there, but you might have the space tunnel, which is like an 8-dimensional piece of space or something that connects, a little bit like a wormhole, that connects something where it's kind of you're here in space, there's a space tunnel, which is a higher dimensional thing, and then you end up in another place in 3-dimensional space. Okay, so with that setup, what might it look like visually if we had the opening to a space tunnel or the opening to a wormhole? I think, I don't know for sure, but I think that it would look like a black hole on the incoming side and a white hole on the outgoing side. So I think what would happen, and I'm not certain, and actually this is something I hope to actually work out, is a black hole is something where there's so much gravity in a black hole that nothing can escape from it, not even light. So everything falls into a black hole and nothing gets out of a black hole. At least that's the first approximation. There's a more complicated story of a phenomenon called Hawking radiation, in which things do come out of black holes. But in the first approximation, things fall in and never come out. So a black hole, that's how it works. Things fall in, never come out. A white hole, we don't know white holes exist. And actually, there are good arguments to say that you can't really ever prepare a white hole quite. But a white hole would be a black hole run like where the movie is run in reverse, where instead of things falling into the black hole, things fall out of the white hole. So it's something where instead of you seeing everything falling in, you'd see everything coming out. So I think that in a space tunnel, what you would see is at the incoming end of a space tunnel, you would see basically everything kind of, or things in space kind of streaming into the space tunnel. At the other end, you would see things streaming out of the space tunnel. And that's, I think, what it would look like, but I'm not sure. And there's a question of whether you would be able to see, like, you know, a periscope, so to speak. Would you be able to see the other end of the space tunnel? I mean, in the thing I've just described, that will be a one-directional space tunnel. You go in at one end, come out at the other. It wouldn't be something where you could go back and forth through the space tunnel, although it's possible that such a thing might exist in space, in the universe. So I would say that in terms of things like space tunnels, there's the question, you know, would you make a space tunnel? I don't know. Maybe there are space tunnels that could be left over from the very early moments of the universe. So if you find a space tunnel somewhere, you might be able to use it. It might be that, you know, there was an old sort of old tunnel that had been made through the mountain, so to speak, that was like, we might find one from, you know, hundreds of years ago or something that was unused. And it's like, okay, now we can use this tunnel. But, you know, can we make one ourselves? The most likely possibility is that it would be some way of taking big lumps of matter, like black holes and things, arranging them in just the right way so that you would create this sort of thing that would exist as a space tunnel in the universe. But I don't know exactly how it will work. And actually, I was thinking I should try and figure that out, because we now have this theory of physics which should allow us to answer whether these things are possible or not. Okay. Let's see, we got all kinds of questions here. All right, let's try, how could one make a force field? That's a good and challenging one. So what is a force field? A force field, okay, so a force field in most sort of science fiction-y stuff is, you know, like in the Star Trek version of the, you know, put up our shields type thing. It's some kind of invisible thing around an object that prevents anything else from getting into that space. So I might have, you know, a force field around my water bottle, and it might be as soon as anything approaches the water bottle, boom, it gets repelled away. So could we make that? So we have examples of things like that. Like if you have a magnet and you try and put the north end, two north poles of magnets, right, you know, you try and push them together, they'll push themselves apart. That's kind of like an example of a force field. There's the you know, the two north ends of the magnet, they'll repel each other. But of course, the magnet will often, if you push two magnets, like one of these very strong rare earth magnets together, if you push them together, it'll tend to flip itself around, and the, you know, the south pole of the magnet will align with the north pole, and those two things attract. So a question is, can you make it so that things always repel? Well, there are different rules for different kinds of things. So for electric charges, there's a rule that says two like charges. If you have two plus charges, they'll repel. If you have a plus and a minus charge, they'll attract. So for electricity, we have this feature that like charges repel. Charges that are the same sign repel. Charges that are reverse of each other will attract. So one knows one other example, which is gravity. In gravity, everything has a positive mass, and gravity is always attractive. There's no repelling form of gravity that we know. Now that raises the question: why is there nothing with negative mass? Why is mass always a positive quantity? You put something on a scale, the scale never says, oh, it's a negative mass. The scale's being pulled up by the thing that's being put on it. Now, of course, things float. When you're in a medium, like even air, for example, you can have a helium balloon that will float on the air because the helium balloon is less dense than air. But if you're in a vacuum where there's just nothing there, then as far as we know, nothing sort of floats on the vacuum. Mass is always positive. It always when you have gravity, which causes masses to attract each other, the force of gravity is always positive. It always pulls things together. Okay, could you have a negative mass object? Actually, this is something that we can address in this physics theory of ours. And the answer is, the answer is, in the structure of the theory, in principle, you can have negative mass objects. In the actuality of making them in the universe, I think you can't. And I think what happens is, in the vacuum, you think you make a vacuum, you're always told there's nothing in the vacuum. Well, actually, that's not true. That's not even true in the standard theories of quantum mechanics and physics that exist today. In the vacuum, there's a sort of a continual activity that we don't notice it because we never have anything which doesn't have that activity. So if we say, let's make a vacuum, we say, well, let's get rid of all the air or whatever else, then we have whatever is left over when we get rid of all the air, and anything else that might be there. But then the question is there something that is sort of fundamentally, can we go even further and can we get rid of the things that are kind of gunking up the vacuum? The things that gunk up the vacuum, there's a thing called zero-point energy. There's what's happening in the vacuum is, well, in our theory of physics, the vacuum, the structure of space is actually created through this kind of network of points that are continually being rearranged and so on. And the fact that we have this idea that there's sort of that the universe is full of space, that we can go from one place to another in the universe and so on, is because there's this whole network of points. And as we move from one place to another, we're basically moving one point to the next, to the next, to the next, to the next through this network. And that network is continually kind of restructuring itself. And it's the average effect of that network that is what seems like space. And space is what the vacuum is what we get when there's nothing except space in the universe, when there are no electrons, there's no atoms, there's nothing like that. There's just whatever is left over when all we have is space. But space itself, at least in our theory, space itself has this complicated structure. In sort of standard quantum physics, in addition, one doesn't really talk about the structure of space, but one talks about things called virtual particles, which are actually, I think, closely related to all of this sort of activity in space. But so anyway, so the vacuum, the ordinary vacuum that you just find if nothing is nothing is there, is still this thing where there's all this activity. Space is kind of reknitting itself, and there are all these virtual particles and all that kind of thing. Okay, so space effectively has a lot of stuff going on in it. If one could somehow clean space out and prevent some of those things that are normally going on in space from happening, then one would have space, then one would have something with negative mass. So in other words, we have kind of vacuum counts as being what we call zero mass. But and when we add things onto that, it's like, oh, we've put something with mass into it. But actually, we could imagine kind of cleaning out the vacuum. If we could imagine doing that, we could imagine sort of, quieting down, getting rid of all that stuff that's knitting together space, all those virtual particles and so on. Then we would have something which is kind of a bubble in the vacuum, and that bubble in the vacuum would look to us as if it has negative mass. Okay, so can we actually achieve that? My guess is no, and my guess is we can't achieve it for the same reason that, it's the same reason that when you have heat in an object, when you have all the little random motion of molecules that gives rise to heat, that the heat doesn't spontaneously, you don't get, if you have a hot object and a cold object, you don't find that the molecules are all bouncing around in the hot object. That's what makes it hot. They don't all, they can flow from the hot object to the cold object. All that random stuff in the hot object can heat up the cold object. But the molecules in the cold object don't line themselves up and all go contribute themselves to the hot object. That's sort of a basic fact about thermodynamics, that heat doesn't flow from colder bodies to hotter bodies spontaneously. And I think that for that same, it's an analog of the same thing, will prevent one from ever being able to sort of clean out a piece of the vacuum. That anytime one tries to do it, there will always be sort of effects that just come in and kind of fill it in, just like one would get sort of filled in by random heats from associated with motion of molecules and so on. So my guess is that it isn't possible to make negative mass. If you could make negative mass, then you would potentially have a repulsive force of gravity. So you could have, let's imagine that you had an object and you could make a layer of negative mass stuff around your starship or whatever. If you could make a layer of negative mass stuff, it will gravitationally not attract things, but repel things. So if you could make that layer of negative mass stuff, then you would have, essentially like a force field, you would have this stuff, whatever it looks like, outside of your starship, and anything that is getting near, any little sort of asteroid that might otherwise be attracted by the force of gravity, will be repelled by a force of gravity from that negative mass thing that's outside of your starship. So that's one kind of, I think that would be sort of the best way to make a force field, is to have a universal, because gravity is universally attractive, if you make negative mass, it becomes universally repulsive, and that would be a way to make, it would work fine until I guess you have a negative mass object. You have two starships, both with negative mass shields outside them, and then maybe there's an attractive force between the negative mass of the two starships, so that makes things more difficult. Another kind of approach to sort of a thing like a force field would be some kind of something with pressure. So, for example, if you want to push something away, you might be able to do that. At a very simple level, you blow on something, and the force of the air coming out of your mouth will push the thing away a bit, because the molecules of air from your mouth are hitting the thing, they're bouncing back, they're transferring the momentum that they got from being pushed out from your mouth. They use that momentum to push the object away. So one question would be, could you create, in a kind of a starship scenario, so to speak, it's kind of not really totally convincing if you have this big sort of tank of gas or something inside the starship, and you say, I'm going to get rid of my, I'm going to repel everything by just, puffing this gas out and trying to push things away like that. Of course, that, it's kind of not unrelated. It's sort of the opposite of the way the rocket engine would work and so on. But, so is there an alternative to that? Well, there's one possible alternative, which is to use something like radiation pressure. So just like, if you have molecules in a gas, you sort of blow them out, and then there'll be a force that they'll produce when they bounce off something. Well, you can do the same thing with light. If you have a flashlight, the flashlight is emitting a stream of photons, and those photons, like molecules in a gas, if they hit a mirror, for example, the photons will bounce back. That's what a mirror does. It reflects. A photon comes in this way, and then the photon is reflected and goes back the other way. When that happens, photons also has some momentum, just like gas molecules and so on. And there'll be a small force that this photon will put on the mirror that will push the mirror away from where the photon hit it. Well, this idea, people have just started trying to use this idea as a sort of propulsion method for spacecraft, because the sun is producing light that's streaming out from the sun. And if you put up a giant solar sail made of reflective material in space, then there'll be a small radiation pressure that comes from photons from the sun hitting the solar sail and bouncing back and pushing the solar sail out away from the sun. So that's a way of generating a small amount of pressure. Now, could you increase the amount of pressure that you generate that way? Could you have a quotes force field that really comes by shining this bright, this sort of bright radiation. Well, the best radiation that we know right now would be, well, electromagnetic radiation, things like radio waves, light, and so on. Could we have an intense enough source of light or radio, for example, that we can make it push objects away, in a really convincing way, like the giant space torpedo is aimed at your starship. Can you push it away like that? Very challenging. I mean, I don't think that my guess is that by the time you reach that level of intensity of light or other electromagnetic radiation, that it would generate what's called vacuum polarization, which is a phenomenon where essentially the actual structure even in standard quantum field theory, the structure of the vacuum breaks down. So for example, if you have a very strong electric field, you'll eventually in air, you'll eventually see breakdowns. So that's what happens in lightning, for example. A cloud has a very large electric charge, and what's happening is it's trying to see whether can that electric charge be conducted down to the ground. And most of the time, the air doesn't conduct electricity. But if you put enough sort of electric force, voltage, across a piece of air, more than, I think, what is it, 1,000 volts per meter? I've forgotten. If you put enough sort of voltage across electric force across air, the air will break down. The atoms in the air will break up, and the electrons that exist in those atoms, which are what you need to make an electric current, will break off from the atoms, and they'll make this electric current. They'll make a plasma, actually, and that's the blue stripe that you see in lightning, is the breakdown of the air. The air will conduct just in that the air will be sort of the atoms in the air will be broken down to the point where the electrons in them can move, and you can get conduction of the air. So the air breaks down. A similar phenomenon happens even in the vacuum. It's called vacuum polarization, and I kind of suspect that to have a level of intensity of electromagnetic radiation to actually have any serious effect on your incoming space torpedo, you would end up, it wouldn't work because of vacuum polarization. So, okay, the most exotic thing we could imagine would be to use gravitational waves as a way to make so just as we can have a radio transmitter that produces electromagnetic waves, so when by moving electric charges around, so when we move masses around, we generate a small amount of gravitational waves. So those hadn't been observed until a few years ago, when there was a merger of two black holes about 1/3 of the way across the universe that was observed. And in a period of about a few seconds, these two black holes, a bit larger than the sun, they're with a bit more mass than the sun, they're actually quite small compared to the sun, they collided with each other and they merged. And that process of the two black holes merging released an immense amount of energy, the equivalent of turning the sun into pure energy in about a second, the whole sun into pure energy in about a second. And that's intense, but that energy went into gravitational waves. Gravitational waves are kind of perturbations in the structure of space-time that sort of propagate like radio waves propagate correspond to electromagnetic fields. So similarly, these are little perturbations in the gravitational field that propagate across the universe. And they got to Earth, and we were able to detect them by this thing called LIGO, which is it's basically a big, long piece of material that when one of these gravitational waves goes through it, it just wiggles a little bit. The ends, it gets a little bit shorter and longer at a certain frequency. And that's the way that you detect that this sort of ripple in space-time has gone through it. And so that was detected about 5 years ago now for the first time. And now these things are seen every few weeks. There's some place in the universe where two black holes are colliding, huge amounts of gravitational wave energy is released, and we can detect it. It's really a remarkable thing to me that an event that is really quite small, I mean, these black holes are maybe a few kilometers across, that a thing that's happening in that localized an area anywhere in the universe we can now detect it through these gravitational waves. But so the question would be, could you make a thing where you're somehow using gravitational waves instead of electromagnetic waves, instead of light, to make your force field? So what you would have to do is you can create gravitational waves by moving masses around. You basically have to deform a mass, the tidal deformation, which means if you have a spherical thing, it has to be elongated and then diselongated, so to speak. You're wiggling it more or less like that. That will generate sort of minimal gravitational waves. They're absolutely tiny. For, my hands moving like that will generate gravitational waves, but so incredibly small that you'd never be able to detect them. But let's say you could do that really aggressively, just like what happened when these black holes collided and merged, that produced gravitational waves. There was so much, when the black holes merge, the two spherical black holes, they merge, they're eventually going to make one spherical black hole. The process of rearranging themselves to make that spherical black hole, that's what leads to this kind of deformation of mass that leads to the generation of gravitational waves. So so imagine we could make gravitational waves, intense gravitational waves. I suspect we could do the same thing that you do in solar sailing, or where you use radiation pressure, light pressure. You could do that with gravitational waves. The problem is you'd have to make intense source of gravitational waves. I mean, the only source of gravitational waves we've even been able to detect is the merger of two black holes. And your friendly starship, so to speak, it's going to be challenging for it to have sort of the analog of black holes sort of lying around that it's able to wiggle in a certain way to generate this this sequence of gravitational waves. But imagine you could do that. A question would be, can you make intense enough gravitational waves to be able to act as a meaningful force field? Again, I suspect the answer is no, because I suspect that if you make the gravitational waves strong enough, that you can actually transfer significant amounts of momentum to actually, deflect that space torpedo or something. My guess is that those gravitational waves will cause the analog of breakdown of the air, vacuum polarization, but in the structure of space-time, and that analog is the formation of black holes. So my guess is that if you wanted to have gravitational waves strong enough to make a force field that can be useful, then those gravitational waves would be so strong that they would be making little black holes in the wake of the gravitational wave. As you train your force field on something, you're generating these gravitational waves incredibly strongly. And as you generate the gravitational waves, they actually wouldn't propagate out very far because they were making little black holes instead. So my guess is no luck on the force field. At least I can't see how to do it. Okay, there are several questions here about warp drive and shields. Actually, I'll mention one thing about warp drive. So, the big idea of warp drive is being able to go faster than light. And as I mentioned, the way that the very structure of space-time is created basically assumes nothing can go faster than light. So it really has to be a deformation in the structure of space-time to create a thing that is going faster than light. But when it comes to, I don't know, I think in the Star Trek, version of the universe, I think that the propulsion mechanism is antimatter, and that is something that can be, to get the starship to go faster than light don't know a way to do that. I think you're talking about space tunnels and things like this, and it's not clear how that works. But in terms of just having a way to propel the spacecraft, how might you propel a spacecraft? Well, how does a basic spacecraft work? A spacecraft works by using essentially Newton's third law, which says to every action there's an equal and opposite reaction. Or alternatively said, if you have your rocket here and it has some fuel inside it, some propellant inside it, gas, and you eject that fuel out of the back of the rocket at a high speed, that will push the rocket forwards. And this is the idea of conservation of momentum. So if you have the momentum is the mass times the velocity, So so if you have a certain amount of rocket fuel and you're squirting it out of the back of the rocket, and you make that rocket fuel go really, really, really fast, then you'll be able to have, then that will push the rocket forwards by an amount, and the rocket, that will, what am I trying to say? I'm basically trying to explain why you can have it be the case that a fairly small amount of propellant that you can store inside the rocket can keep pushing the rocket forwards for quite a while, so to speak. But in order to get that propellant pushed out of the back of the rocket really quickly, you need to have you need to put a lot of energy into the propellant. You need to make the rocket fuel go really, really fast. And the way that's achieved in a traditional rocket is through combustion, through essentially burning. So what you do is, so a simple case is you might have liquid hydrogen, liquid oxygen in two different tanks in the rocket. And then you bring those two together, and there's a chemical reaction between them which actually produces water, because water is H2O, and that's the end result of combining hydrogen and oxygen. But the process of going from separated hydrogen and oxygen to water is one that releases lots of energy, because essentially the hydrogen and oxygen, when they're bound together in a water molecule, they have that binding energy. You sort of trade off the binding energy for actual energy of kinetic energy when you produce the water molecule and so on. What's basically happening in your average rocket engine is you're combining some fuel together with some with something. You're essentially burning something, like you're burning the hydrogen in the oxygen, or you're burning some solid fuel in something like oxygen. And that's a chemical reaction which releases energy. And usually the big challenge in a rocket is you've got this combustion chamber, usually a spherical combustion chamber, you've got a nozzle at the back. Usually the big challenge is, can you get fuel into that combustion chamber fast enough to actually produce, to actually have the combustion run really quickly and have the fuel come out of the back of the rocket fast enough. And there's usually a turbo pump that is trying to pump fuel into the combustion chamber. That's usually what limits the efficiency of rockets, is how fast you can pump stuff into this combustion chamber. And it's very complicated, because you see a typical rocket engine, it's full of all these weird tubes going in all different places, because the properties of these gases as they combust change a lot depending on their exact pressure and temperature and so on. And you have to kind of take account of that and have all these valves that control all sorts of things. And that's kind of why it's hard to make a rocket engine. But basically the idea of a rocket engine is you're generating energy by essentially burning things. And the nozzle at the back, actually the nozzle is sort of opening out, because it turns out there's a weird property when you have a gas that is traveling at hypersonic speeds, maybe more than 10 times the speed of sound. It actually, normally with a gas, you think if you want to make it go faster, put it in a smaller, more constricted area. But for hypersonic gases, it actually works the other way around, which is why you can make it go a little bit faster by sort of opening it out like that. But anyway, so standard rocket, chemical combustion produces high-speed gas that shoots out the back of the rocket. Okay, so what other methods could you use to make to do something like that? Well, one thing you could do, there are things called ion rockets, and the idea of an ion rocket is you have a source of electrons or ions, atoms that have had their electrons stripped off, but so they're electrically charged, and you have something which attracts, because I mentioned, when you have, let's say you have a negatively charged plate here, and you have a source of positive ions here, then the negatively charged plate will attract the positive ions. If this is a grill or something where they can go through, you have the source of ions, they go through, they're sort of attracted to this plate or this grill, then they go through the grill and they get sort of sent out the other side. And you can make a rocket engine that way, because you're essentially using electrical forces to go and accelerate the electrons or ions or whatever. They get accelerated and pushed out the back of the rocket. And actually, people make small thrusters for rockets using ion engines, And just like you use up sort of the hydrogen, oxygen, or whatever it is in liquid, in propellant, in a standard chemical rocket, in an ion rocket, you're using up whatever your source of electrons or ions or whatever it is to make that thing that's pushed out of the back of the rocket. Okay, so what other kinds of ways could you make a rocket? Well, one way you can make a rocket is with nuclear power. And there was a big thing in the 1960s. People thought nuclear rockets might really be a big thing. Nuclear power involves taking the nucleus of an atom and, for example, using the fact that, being able to, when the nucleus of an atom of a sufficiently heavy element like uranium comes apart, it releases energy in doing so. And so, and that happens, you can, in an atomic bomb, that happens very rapidly. In a nuclear power station, that happens in a much more controlled way. The equivalent of a nuclear power station is used in submarines, for example, where there are nuclear submarines which are powered by having a nuclear reactor. And the nuclear reactor has a small amount of fuel, uranium, plutonium, typically, what's happening is there are those nuclei are kind of falling apart. As they fall apart, the products of them falling apart cause other nuclei to fall apart, and that produces this kind of chain reaction that in the case of a nuclear power station or a nuclear submarine is a controlled nuclear reaction, but it releases energy. And so it's using up small numbers of atoms. Every atom that it kind of uses up produces a certain amount of energy, but it's actually a very large amount of energy compared to the amount of energy that you would get by having a chemical reaction producing energy. So another scheme is to use nuclear power for rockets. As I say, that was kind of a thing that people thought about in the 1960s. The problem is it's sort of a super bad idea to have sort of serious nuclear things, particularly things that can turn into nuclear weapons in Earth orbit, because a very bad thing happens. If you detonate a nuclear explosion in space, it's never really been done, but it's been there've been detonations in the 1950s. There were nuclear explosions that were detonated over the Pacific at a decent height, but not all the way in space. If you detonate a nuclear explosion in space, the thing that happens, okay, so you detonate a nuclear explosion in the atmosphere, you are producing, you're kind of exploding and you're pushing the air away and you're making a shock front from the air being pushed away. Well, in space, there's nothing to make a shock front out of. It's just a vacuum, so that's not what happens. What happens instead is that you have a lot of radiation that can be, it's light, it's X-rays, it's gamma rays, it's any kind of electromagnetic radiation gets produced by this nuclear explosion, and that all streams outwards from wherever the explosion happened. But one of the things that's produced is not only light and X-rays and gamma rays and so on, but also radio waves, intense radio waves, and in particular, this thing called the EMP, electromagnetic pulse, which is kind of an intense sort of one-shot radio pulse. And the issue with that is it's a very intense thing produced by the nuclear explosion, and any piece of electronics that is sort of anywhere near it, when that radio pulse, when that very intense pulse goes through the electronics, it will essentially produce something like that electric breakdown that I was mentioning for lightning before. It will essentially destroy that electronics by essentially producing a voltage inside the electronics just by virtue of the electromagnetic pulse going through the electronics, and will destroy the electronics. So if you have a bunch of satellites, as we do now, in whatever it is, 20,000 satellites in Earth orbit or something, and there's one electromagnetic pulse produced by nuclear explosion, then any satellite that isn't shielded by being kind of in the shadow of the Earth basically has its electronics fried. So that's a sort of super bad thing that happens in that case. So that's one of the kind of, it's a bad idea to have nuclear stuff in orbit, and so nuclear rockets haven't really been much of a thing. I should say, if you're the deep space probes, the ones that went to, for example, outside the solar system, the Voyager and Pioneer, Pioneer 10, 11, that went out of the solar system, it's now like, what is it, 30 times the distance? No, how far is it? I've forgotten. It's those are the things that humans have made that have gone furthest. They've been going for like nearly 40 years now. Going out from the sun, out of the solar system by now. But one of the questions is, how did they get power? Because usually, satellites, they typically have solar panels. They're getting light. They're getting power from light. But when you're far, far away from the sun, that doesn't work anymore. And so what was done for those deep space probes was they used what's it called? Well, they basically use the fact that radioactive decay produces heat. It's not a nuclear reaction in the sense of something where there's a chain reaction where one a nuclear disintegration produces another nuclear disintegration, a big chain, like in a nuclear reactor or a nuclear explosion. Instead, it's just every individual nuclear decay that just happens spontaneously in any radioactive material produces a certain amount of heat. And so what these things had was radioisotope. They were things where they had this radioactive material that was put into the spacecraft. It's actually out typically on an arm so that the radiation from the radioactive decays doesn't affect the electronics in the main part of the spacecraft. But and it uses the heat that comes from that radioactivity to converts that heat into electricity to power the spacecraft. Okay, so anyway, but that's not nuclear reaction, it's just spontaneous nuclear decay that's used for that. Okay, let's go back to the Star Trek type thing. So there's another level of kind of use of nuclear-like stuff that you could do, which is to use matter-antimatter annihilation. So I think I mentioned on another one of these live streams that the idea of antimatter. So to every particle, like a proton, there is also a particle called an antiproton that is the opposite, that has the opposite charge to a proton, has the same mass, because mass is always positive, but the charge of an antiproton is minus the charge of an ordinary proton. If you bring a proton and antiproton together, they will annihilate each other. They'll produce a bunch of other particles, typically a bunch of photons, things called pions, various other things, maybe some electrons and positrons as well. But they'll annihilate. So all of the energy that's tied up in the mass of these protons gets turned into raw energy. So it's a very efficient way of taking. If you could get enough antimatter to do this, you would have a little bottle of antimatter, and you would take that bottle of antimatter and you would combine it with matter, and they will annihilate each other, producing a bunch of energy. Okay, so one of the questions is, how do you get antimatter? Well, there is a certain amount of antimatter produced in particle accelerators. You can get, the easiest antimatter to produce is anti-electrons, which are called positrons. And usually the most common way to do that is if you sort of make an intense X-ray, you shine it at a material, you will get electron-positron pairs made. Electrons and positrons as a pair get made, and then you can sort of capture the positrons, like you can filter them off by using a magnetic field, because in a magnetic field, the particles with opposite charges will go in opposite directions. So you can kind of filter off the positrons. So in big particle accelerators, one of the goals is to have a beam made all of positrons. And that's done by essentially creating the positrons, filtering them off, and then arranging them with magnets to go in this beam. Actually, the sort of the fanciest thing is antiprotons, and the biggest particle accelerator in the world, the LHC in Geneva, Switzerland, it has a beam of protons inside it, and it also has a beam of antiprotons. And it's a big engineering adventure to basically produce antiprotons. You produce them with proton-antiproton pairs, and then to filter off the antiprotons, to what's called cool the antiprotons, so they're not all going in random directions, but they're all going in that one direction you want them to go in the beam of antiprotons. And then you accelerate the antiprotons around this big circular ring that's a few miles across. That is the particle accelerator. But anyway, so the result is there's a small number of antiprotons that are produced there. Okay, so how do you keep, if you have some antiprotons, let's say I had a bottle of antiprotons, how would I keep a bottle of antiprotons? Because as soon as I have if I just put them in a metal box, that metal box contains a bunch of protons, because that's what's inside the atoms that make up the metal box. And so as soon as any of my antiprotons come into contact with the protons, bam, they annihilate, and no more antiprotons. So how do you keep antiprotons in a box? What kind of box can you keep them in? Well, there's one kind of box that will work, which is essentially a magnetic box, because photons don't, it's basically because photons are their own antiparticle. Photons, an antiphoton is just a photon. And photons are what, in a sense, make electromagnetic things. And so you can imagine something where you have a bunch of magnetic fields where you're kind of keeping these antiprotons in this kind of magnetic bottle where there's no material, there's no atoms or anything that are inside. It's kind of like a force field, but it only works, that force field only works for these particles, these antiprotons that have a definite electric charge. If you ever threw something in there that had a different electric charge, the force field wouldn't work anymore for it. But when you just have these antiprotons in there, you can make a magnetic bottle that keeps the antiprotons in there. So kind of in the Star Trek concept, it's kind of like you keep a bottle of antiprotons and you're gradually letting those antiprotons out and letting them annihilate with protons, and bam, that makes a lot of energy every time that annihilation happens. Now, having said that, you might say, has anybody actually made a bottle of antiprotons? The answer is not really. They've made ones with a very small number of antiprotons. This whole process of confining things with magnetic fields is a very difficult process. So that's not really been a big thing that's been done, but it's certainly in principle possible. Okay, we got all kinds of questions here. Let me take a look at a few of these here. Okay, there's a question here about are there universe hacks that can be done based on our sort of emerging model of how fundamental physics works? Don't know yet. Been wondering about it. My guess is the places where there might be, quotes, universe hacks have to do with things to do with quantum computers, some possibly the space tunnels thing, possibly some things to do with particles that are much lighter than electrons and that kind of go through every kind of material and so on. That's the current thinking. But I think it's a bit of a challenging thing, because if you started off from, I don't know, the early theories of gravity from 300 years ago, and you said, what are the gravity hacks that you might be able to implement to do with, having, spacecraft that are going to other planets with these complicated maneuvers where they slingshot around Jupiter or something to get enough momentum to go out to other planets. I don't think one would have had those ideas in the first few weeks after Newton's universal gravitation idea emerged. So these are things that have to develop after one really understands these theories better. Let's see. Questions about extraterrestrials. Let me come back to that if we it's a slightly complicated answer, I think. Okay, there's a question here. Do I think an organism living its whole life in three-dimensional space could survive entering a higher dimensional area? I've wondered about that. I have a bad feeling that it's impossible. I have a bad feeling that if you are, if you were a creature that lived on a two-dimensional plane, maybe you can keep going, sort of living in that two-dimensional plane, even in three-dimensional space. And maybe the same thing could happen if you're, if there's some space tunnel that's a six-dimensional space tunnel or something, and we're just these poor three-dimensional critters. I'm not sure though, and I have a slightly bad feeling about that it might not work. Because what happens in black holes, for example, is you tend to get there are very strong gravitational fields, and what's worse, a gravitational field would like pull you into the center of the black hole, but there's a much worse thing that happens, which is the tidal forces. So what happens is if your head's going that way and your tail's that way, so to speak, your head is, and here's the center of the black hole. Your head is closer to the center of the black hole. Your feet are further away from the center of the black hole. The force of gravity on your head is proportionately, because you're closer to the black hole, is stronger than the force of gravity on your feet. And so what that will tend to do is to elongate you in the direction in which you're being pulled. And that happens on the Earth, for example. The gravity of the moon will make, if you look at the oceans on the Earth, that's why it's called tidal forces. The oceans on the Earth, the water that is on the side of the Earth that's closer to the moon is proportionately pulled further up, and the water that's on the Earth, the opposite side from the moon, is sort of goes further away, and that so in effect the Earth is getting slightly elongated by the presence of the moon. Actually, that happens both with the oceans on the Earth, and there's also things called solid tides, which are a deformation in the actual shape of the Earth and the rock in the Earth as a result of that gravitational effect. But that effect gets very strong around a black hole, and so the technical term, I think, in the black hole business is spaghettification. Everything gets turned into kind of long pieces of spaghetti because everything is elongated. It's sort of infinitely elongated between its head and its feet, so to speak. So things like that might happen. Let's see. Gosh, a lot of interesting questions here. Hold on. Let me just read through here and just get okay, there's a sophisticated non-kid discussion here about space tunnels and sheafs of geodesics in space tunnels, which looks interesting. But let me not go there right now. Okay, there are questions about teleportation. Okay. Yeah, okay. So, lots of interesting questions here. Let's see. Let's talk about, the end of the universe for a moment. So we don't know what the end result. So the universe is expanding, and right now we don't know whether the rate of expansion of the universe is going to stay constant, whether it's going to eventually decrease, maybe even turn around and the universe could start contracting again, whether the expansion of the universe is going to get progressively faster. People have been trying to measure that in recent times, and there's a slight suggestion that the universe is accelerating in its expansion. Now, it's a little bit, why does it accelerate? Actually, it has to do with the whole negative mass business that I was talking about earlier. There's this thing called dark energy, which is kind of a way of describing the fact that the universe sort of behaves as if there's negative mass everywhere in the universe. It's a slightly weird thing, and it really just sort of feeds into a bunch of mathematical equations. But the question is, what's eventually going to happen in the universe? Is the universe eventually going to, what will happen? I mean, the universe is so far about 15 billion years old. The Earth is about 4.5 billion years old. The sun might survive another 5 to 10 billion years. And eventually will turn into a white dwarf star. It won't do anything terribly violent. It won't have a giant supernova explosion. It won't turn into a black hole. It's not, it'll just sort of quietly sort of fizzle out and turn into a white dwarf. The thing that, so the question is, what will happen sort of in the very, very, very long term of the universe, billions of years in the future? So one of the things that's happening in our galaxy is our galaxy has about 100 billion stars in it. At the center of our galaxy, there's a giant garbage dump, basically. There's a giant black hole. I think it's about 100,000 solar masses in mass right now. I think it's a black hole. Is that right? Maybe it's slightly less than that. It's a black hole that's slowly absorbing stars, and so it's like garbage disposal at the center of the galaxy. So over time, eventually more and more stars will fall into that black hole at the center of our galaxy. And presumably, over time, more and more of the universe will just turn into a bunch of giant black holes. Now, and presumably, as the universe, well, okay, so in the scenario where the universe keeps expanding, that's probably what will happen. Now, there's a little footnote to that, which is that because of this thing I mentioned called Hawking radiation, black holes eventually evaporate. Eventually, a black hole, even though you thought black holes just absorb things, actually, as a result of quantum effects, and as a matter of fact, one can see this very beautifully in this new theory of ours, how this works. As a result of quantum processes, there's a slow rate of particles coming out of black holes as well as things going into black holes. So in the very distant future, these black holes that are sort of formed from centers of galaxies will eventually evaporate, and they'll produce a bunch of material, a bunch of particles in the universe. And what will happen to those particles is not completely clear. Those particles might be subject to the force of gravity, and they might start forming a new generation of stars and galaxies and other things. It's not completely clear. Okay, so right now in the current measurements, okay, so one possibility is that that sort of the universe gets very boring and it's very, very quiet and it's just a bunch of black holes. Eventually, the black holes evaporate, then things might happen. Another sort of generation of stuff might happen. Another possibility is that the universe will sort of slow down and eventually start contracting again. And the universe started from a big bang at the beginning. Maybe it ends up with a big crunch at the end, and it's sort of reprocessed, and all the stuff in the universe is kind of reprocessed in another kind of big bang after that. A little bit like what's happening in these black holes, where things come in, they sort of get reprocessed in the black holes, and eventually get emitted again as Hawking radiation. So the other possibility is that the universe is progressively accelerating, and that eventually the universe is that there's the edges of the universe are going faster than the speed of light. And how that works, I said nothing can go faster than light. It's slightly complicated because one has to ask the question, how does one know sort of what time it is where in the universe? And when you unravel all of that, you realize that if you were to look from outside the universe, you might see it expanding faster than light. But from inside the universe, you never detect that phenomenon. So you can't kind of you can't hitch yourself, you can't hitchhike on the expansion of the universe, so to speak, to do that. But what happens in this accelerating thing is that sort of things eventually become so dispersed in the universe that sort of nothing can kind of communicate with anything else. Well, yeah, so there's a question here. Would it be possible for an intelligent species to create the conditions to create a new universe? Oh, this is a complicated story because, okay, what we currently believe in our theory is that the universe is ultimately a computational thing. The universe is running these rules that just say how space is created, how everything else is created. But the difference between like running those rules in a computer that we've constructed and the universe running those rules is quite a big difference, because we could run those rules, we can simulate what the universe would do, but what's going on in the actual universe is it has actualized those rules. It is behaving according to those rules. It's not that it's running those rules on a computer. It's just those rules are describing how the universe works, and the universe is working according to those rules. So you can ask questions like, given the rules for the universe, can you sort of re-implement them on top of some other part of the universe, like you re-implement them in a computer? Could you re-implement them in some other part of the universe so that you effectively have a simulation of the universe running inside the universe? The answer is yes, you can imagine doing that. You will, in any way I can imagine doing that, you lose unbelievable amounts of, like it might be, 10 to the 100 times slower to do the simulated universe as compared to the actual universe. So, I think that's so I'm kind of, the question of how do you create something, I think in our theory of how the universe works, the universe just follows a certain rule, and it just does what it does. And everything about what's happening in the universe is in a sense determined by that rule. I mean, the words I'm saying now are sort of ultimately determined by the rule that runs the universe. And you don't really have any choice about that. It's just the universe is going to do what the universe does. We don't get to sort of be outside it and ever change what it does. It is inexorably going to do what it does. Now, how we choose to exist in that universe is a whole different story. So, for example, so somebody was asking earlier about sort of the long-term future of humanity. And, right now we exist as kind of, biological organisms with electrical signals in our brains that cause us to think things and so on and so on and so on. But it's not clear that if you want sort of the essence, whatever the essence of sort of human consciousness or whatever is, it's not clear that the only implementation medium for that is humans with biology and brains and things like that. Now, you might say, what does it mean to be a human if you don't have, your whole sort of biological body around? Not clear. It's not, I think that's something that will get worked out probably in the next 100 years or so, in the trajectory we're on right now, as it becomes so, the thoughts that go on in our brains are essentially encoded in electrical signals in the nerve cells in our brains. And there is that pattern of thoughts is something that we could run it on a computer, we can do all kinds of things with it. That pattern of thoughts is not specifically tied into the particular biological implementation with our, nerve cells that are using glucose to fuel themselves and are, doing all these kinds of things that are all of what we are used to doing in biology. There is a sense in which that pattern of electrical activity is just represented by, a bunch of bits of information that are representing how we're thinking about things. So, people imagine in kind of a sort of science fiction way this notion of uploading human consciousness to a machine. So, our brains have about 100 billion neurons probably in them. It's kind of hard to tell exactly how many because they're very mushy and it's very hard to count neurons because they're very long, spindly things with a lot of connections to a lot of places. But roughly it's 100 billion. And these neurons are all very interconnected. There may be 100 trillion connections between all these neurons in our brains. So, and presumably, we don't know absolutely for sure, but it looks super likely that all of our memories, everything about sort of who we are, is encoded in those connections. So those 100 trillion connections are representing, each one of those connections has a certain has a sort of a bit of information associated with it. And so we're kind of storing maybe a terabyte of information in our brains that represents sort of all of our memories and all the things that we do to sort of figure out to have our brains operate. And that's kind of the computational structure that corresponds to our brains. Now imagine that we implement that computational structure not using biology but using some other medium like digital computers. We're not that far away from being able to simulate what happens in a brain. We're maybe, maybe 1,000 times, maybe 10,000 times away, depending on exactly how efficient or inefficient brains are. Brains are probably pretty inefficient compared to what we could create with modern engineering and so on. But so, and like, for example, it's worth realizing that our neurons in our brains, when a signal goes from one neuron to another, it takes maybe a millisecond or something, a thousandth of a second. Whereas when a signal goes from one part of a computer to another, it takes a billionth of a second. A million, so it's going a million times faster than the stuff in our brains. So it's not clear quite how far away from being able to sort of emulate what's in brains we really are. And it's also not clear the details. So people make in AI, artificial intelligence systems, people make these things that are called neural networks, which are kind of a simple computational idealization of the way that actual neural networks work in brains. And it looked like they were a pretty bad idealization. They weren't really a good model for how actual neurons work. But actually, it turns out it doesn't seem to matter much that it isn't a good model. The same kinds of learning processes that happen in actual brains with actual neurons seem to be able to happen in these artificial neurons, even though the artificial neurons are not really emulating all the details of how our neurons in our brains work. So it's quite possible that the kinds of even artificial neurons that we have right now could be able to be sort of the carriers of activity that are like the activity that goes on in our brains. And so, one question is, okay, I'm going to make the digital version of me, the me bot. How do I do that? Well, you kind of have to, presumably, it would have to learn through all the kinds of experiences that that I have and so on. It would have to see, it would have to learn just like I was mentioning this at the beginning here. I mean, there's a certain amount of built-in information in our brains. There's a certain amount of built-in structure in our brains. The way like the visual cortex at the back of our brain works, the details of seeing a cat or a dog, those are not built in. But the overall structure of the visual cortex is determined by the way our brains are built. And the overall fact that, there's some places, well, actually, even that is not quite so built in, but there's features of the visual cortex that are sort of built in as a matter of the construction of the nerve cells that aren't things that are learnt by us in our lives. But ignoring that, much of what's there is just learnt from the course of our lives. So sort of a question is, if you're going to make a digital bot of yourself, how much information do you need to do that? I mean, I've kind of wondered for myself, as I record all these live streams, and I've recorded my email for 30 years, more than 30 years now, and I've recorded all the keystrokes I type and all sorts of things like that, just because I think it's fun to keep all that data. There's a question of, is that in fact enough data to reproduce me? If you had a neural net and so on, or some system that was big enough, could you just play back my email experience for the last 30 years and have something which say, oh yeah, I've learned from what Stephen does here and there. I've learned what he does, so I can kind of reproduce what he does, and then you have something which is kind of the me bot, so to speak. And is that possible? I think that will be possible. How much? I think that and there'll be all kinds of complicated questions then. I mean, in other words, I don't know. Will I get on with my me bot? Unclear. I don't know. I'm not sure I would get on well with an exact copy of myself. And then there are all kinds of questions like, people were talking about teleportation. It depends on what form. If to teleport a material object is one thing, to teleport a digital representation of a brain is quite a different thing. I mean, by the way, it's worth realizing when one talks about teleportation that there's one thing is to take the atoms that are in you and move them somewhere else. But, every atom of hydrogen is the same as every other atom of hydrogen. And, every electron is the same as every other electron. So this question of how do you move something from here to there? Well, if you could say, I'm going to figure out where every atom in the thing that I've got coming into my teleportation device, how every atom is arranged, I'm going to take that information about how every atom is arranged. I'm going to send it. I'm going to send a light signal, for example, the speed of light. I'm going to send the signal that's just all this data about how all those atoms are arranged. And at the other end, I'm going to have a little device that reconstructs where all those atoms are placed. Well, then you can have no material passed from one place to the other, but nevertheless, you had the result of going from one place to another, let's say at the speed of light. So now, but you have all kinds of weird questions. Like, for example, if the device that was reading the thing coming in, maybe it was a brain, maybe it was a frog, maybe it was who knows what it was, reading the thing coming in, did it destroy the thing coming in when it read it, when it figured out where every atom is? If it did, then what it's going to look like is you destroy the frog turns in, you just have a description of where all the atoms in the frog are, you move that description to somewhere else, and you reconstruct the frog. That's model number one. Model number two, you have a very clever way of reading out where all the atoms in the frog are, and actually at the end of it, you have two frogs, one at the one where it came from, and one where it was reconstructed at the other end. So there are a lot of weird questions about when we think about that. For example, for humans, a lot of weird questions about human identity and so on that come up, and there will be a lot of questions about whether sort of disembodied human consciousnesses, what kinds of to what extent they are like the human, and to what extent they should have rights like humans and things like this. To what extent are they merely merely sort of the creation of the human and don't have the same character as the human themselves? And there are a lot of interesting questions there, and a lot of things about if you have a disembodied human consciousness, is it okay to destroy it? Even if it could never be reconstructed, is that a terrible thing to do, or not? Well, it's just a bunch of bits, and right now, erasing a hard disk in the normal course of events, it's like nobody thinks it's well, it might be that there's something on the hard disk that you really want to keep, but it doesn't have quite the same characteristic as getting rid of a human. It's just like, oh well, we erased that data. So anyway, okay, I'll take one or two more questions here, and then I should wrap up and go try and figure out stuff about our actual universe. Yeah, I think this question about simulated consciousness and this kind of uploaded human consciousness, and whether that's the end point for us humans, I mean, that's an interesting question, and I think there's a certain inevitability to that. I think that there is a big question if you are going to sort of exist as a simulated consciousness in a in this sort of inside this kind of computer. What do you choose to do with yourself? Because we all get motivated to do the things we do for different reasons, but a lot of those motivations are a detailed consequence of the way that we lead our lives today as humans walking around eating things, living, dying, etc. It's a very the way that we get motivated to do things is a consequence of the sort of cultural environment in which we find ourselves. And if our cultural environment is we're in this kind of digital box as a simulated consciousness, it's not clear what the motivations are. So, for example, a lot of what happens, there's a lot of kind of things that are driven by the scarcity of resources in the world. The fact that the fact that something can be of higher value because there's less of it, and people are prepared to pay more money to get that thing when there's less of it. In a situation where everything is just digital, that type of scarcity would exist only in a very different way. And I think sort of a bunch of questions about how does human society effectively, to what extent is human society dependent on the existence of a limited amount of limited human lifespans, limited numbers of humans, limited all sorts of other characteristics of people having to what extent does the current set of human motivations and the current structure of human society depend on those very physical constraints, and to what extent is it sort of an inevitable logical consequence of just having entities that exist together? So, for example, it might be the case that as soon as you have entities that exist together, you will have a there's you might have I don't know. It's kind of hard to imagine, well, there sort of might be preferred real estate because it might be, well, I want to be in this part of this virtual space that's nearer my friends. And I can only have a certain number of, just because, not because of the structure of the kind of the virtual space, but because, for example, I can only process the information associated with having 10 good friends. And so if the 11th person wants to come and be a good friend, well, I can't do that because I can't process the information associated with that. And if I could process the information, so there's a sort of a complicated circularity to how you think about whether sort of the structure, whether certain features of human society are dependent on the details of the way that our actual physical world works or not. I mean, it's back in the day when people were thinking about money, for example, there was a long period of time in human history where money was where $1 meant you could go to the bank of the country and say, give me a piece of gold that is, that dollar you gave me is just a thing that says I'm entitled to get a piece of gold from you. And for a long time, people sort of thought that money fundamentally had to be backed by actual gold that had some scarcity and was worth something. And then it was realized that actually money is a much more abstract thing that doesn't have to be backed by actual physical stuff like gold that's worth something. And so there's a question, as one thinks about kind of the structure of society, to what extent are the things that we currently imagine are tied to certain kinds of physicality really things that are tied to physicality or not? I mean, like, for example, if you're operating a democracy and you say, one person, one vote. Okay, great. So now imagine that we've got digital consciousnesses and every digital consciousness can make 1,000 copies of itself, okay, or 1,000,000 copies of itself. Well, then this, one person, one vote, it's like, how does that work? This thing just made 1,000,000 copies. Oh, that one made 1,000,000,000 copies. How does that work? Well, I suspect that in that particular case, that in the end, that unravels itself and it doesn't really matter that you can make all these copies. But then, I'll give you another example of something that gets really tricky, is right now we have the notion of, there is a definite notion of a person. There's an entity which is a person, and it's not kind of there's either there is a person or there isn't a person there. Oh, there is a person responsible for that, or there isn't, so to speak. But when you imagine these sort of digital analogs of people, it's a little less clear whether it's person or no person. It's, can there be kind of a sort of a pseudo person, a fractional person, so to speak? And how does that work? And then a lot of the structure of counting doesn't work anymore for people. And there's just it's quite an interesting thing to try to imagine, what aspects of society depend on physicality and what are sort of inevitable. There are features of, I don't know, voting systems and things that might be quite abstractly work that way, or certain aspects of economics that may completely abstractly work that way, independent of any physicality. I don't think we really know which ones work which way. All right, I think we should wrap up there. Well, this was fun for me. I hope people found this interesting. It's, usually one of the downsides of doing science is we have a particular universe that we've been thrown. And when you do science, you're trying to sort of unravel how that particular universe works. What's sort of fun about sort of the science fiction idea is you get to say, well, even in our, what's logically possible, even independent of our universe or the way that we exist in our universe, the way that we, we exist at a certain size and time scale and so on in our universe. All right, well, I should wrap up there. So thanks a lot. And I hope I'll next week, I'll pick a slightly different topic and we can talk about that. And please do give us feedback. And, I have fun doing these things, but let us know what works and what doesn't. Thanks a lot. Okay, bye-bye. Have a good weekend.